This is section 1.5, pre-calculus, and we're going to be doing the combinations of functions along with being able to state domain. You should be on page 13 of your packet. All right, we have dealt with combinations before. It's just a matter of evaluating functions, substituting with other functions. We're first going to look at just some basic operations. So if I'm asked to do, first of all, my example is f of x equals x squared plus 2x, and g of x is 2x plus 1. It says find the following and state the domain. So if I'm wanting to do, let's say, f plus g of x, this is the same as saying what is f of x plus g of x. And that's the case for all four of these operations. So all we have to do is add them together. Let's go ahead and do x squared plus 2x plus 2x plus 1. You add like terms. I've got x squared plus 4x plus 1. All right, so what we need to do is after adding here, we need to figure out the domain. Well, this is just a polynomial, and we know that polynomials, domains, are all reals, so from negative infinity to positive infinity. We're going to do the same thing for here for subtraction. We've got x squared plus 2x. Subtract the second function, but since it's more than one term, we are going to use parentheses. So we need to subtract both of them, and what that really is then is it's a change of sign, so I can add the opposite like that. Okay, go ahead and adding these together. X squared, final answer, x squared. 2x plus negative 2x go to 0, and then it's minus 1, so minus 1. There's our end result here. Again, this is a polynomial, and polynomial's domain would be from negative infinity to positive. All right, f times g of x. We need to multiply now. X squared plus 2x. I'm just going to show the multiplication, which is going to be binomial times binomial. Foil these, you get x squared times your, let's try that again. You have x squared times 2x would be 2x to the third. X squared times the 1 is plus x squared. 2x times 2x is 4x. And then 2x times the 1 is 2x. This would be 2x times 2x, 2x squared there. And then plus your 2x. Combining my like terms, 2x to the third plus 5x squared in the middle plus 2x. There's the product of f and g. Now looking at the domain, again, this is still a polynomial, so my domain is staying the same. You only have to have a red flag on domain when you're dealing with square roots or any nth root that's even, and fractions. All right, the last one here, division. So my f function is x squared plus 2x. And my g function is 2x plus 1. There's really no simplifying here for me to do. I mean, you could factor out an x on top. If I factor out an x on top, I'm left with x plus 2. But that still doesn't help me with anything on the bottom. They are different expressions. So this is just my final result here. Either one of those would work. Now domain. Your domain of this function, because it's in the denominator, the 2x plus 1, you set 2x plus 1, and this cannot equal 0. So then that concludes that x cannot equal negative 1/2. So the rest of my domain would be from negative infinity to negative 1/2 in union with negative 1/2 to infinity. So together, there you go. All right, that's the 4 operations with 2 different functions. Now what we're going to look at is we're going to dig into a little bit more of the domain and compositions. All right, domain. The domain of an arithmetic combination of functions f and g consists of all real numbers that are common to the domains of f and g. In the case of a quotient, there is a further restriction that g of x cannot equal 0. So in a case like this, if you are dividing here f of x divided by g of x, then the function of g cannot equal 0, which we just did that in the last example. All right, compositions of functions. The composition of function f with the function g is called f. This means of f of g of x. It looks like this, f of g of x. It's a way that we substitute a function into another function. We're evaluating. The domain of f of g is the set of all x in the domain of g, so the set of all x in g first, such that g of x is in the domain of f. So we got to pay close attention to the domain of g and then make sure it still follows for the domain of f. We'll look at a couple different examples here. All right, I'm going back to the same f and g function, and let's find the composition. So this is what this means. This means f of g of x. That's the way that we verbally say it, which is asking us to evaluate the function of f at 2x plus 1, since this is my g function. Here's what it would look like. 2x plus 1 squared plus 2 times 2x plus 1. You're going to FOIL this. That becomes 4x squared, 2x twice, so that would be plus 4x in the middle, and 1 squared is 1. We're going to distribute the 2, plus 4x plus 2. Combine my like terms, 4x squared plus 8x plus 3. So this is my final answer. The composition of the function in my domain would be from negative infinity to positive infinity, because the domain of g is all reals. Even after I substitute it, we still have another polynomial that's all reals. All right, going the other way around, g of f of x. So I'm substituting into the function of g x squared plus 2x. Looks like this, 2 times x squared plus 2x. And you still have the plus 1. So this is the function now that I'm substituting in for right here. I'm putting the f function in for the function of g. And as an output, I've got 2x squared plus 4x plus 1. They're both polynomials. In fact, all of these are polynomials, which indicates that my domain is, again, all reals, so from negative infinity to positive infinity. All right, that's how you do compositions. When you do f of g of x, you put g of x in for all the x's. And then when you do g of f of x, you put f of x in for all the function of g. Let's try this one. We've got if f of x equals x squared minus 9. All right, so we've got, this is my function of g. This is my, or f. This is my function of g. We're finding f of g of x. So f of g of x is the square root of 9 minus x squared. This is what we're going to go ahead and evaluate. All right, so I got to put this into the function of f. It looks like the square root of 9 minus x squared, squared, and then minus 9. You take the square root of 9 minus x squared and square it, and you get 9 minus x squared. Minus 9, our result is negative x squared. Now, here's how this is going to work though. My domain depends on the g of x function. My g of x function, the domain here, because I'm asked to state the domain in the next expression here, or next step, Because it's underneath the square root, we have to have this be greater than or equal to 0. So then we've got negative x squared is greater than or equal to negative 9. So x squared is less than or x squared is less than or equal to positive 9, which concludes that x is less than or equal to plus and minus 3. Now this is when we get more than one answer. So we use a number line, negative 3 to positive 3, and we have to decide which ones are true or false. So if I put negative 4 in, this creates an error, undefined, and if I put positive 4 in, you also get an error. So this basically is showing us if I put 0 in, then I get the square root of 9, which is 3 and negative 3. So basically my domain falls anywhere between negative 3 and positive 3. That's my domain. From negative 3 to positive 3. And obviously that also works for the original function. Okay. Finding f of 0. Finding f of g of 0. What I can do now is, since this is f of g, I can put the 0 into my expression that I found. So f of g is equal to 0. Negative 0 squared. All right. There's a true composition here where you have to deal with your domain because of my original function. I had to restrict my domain. All right, let's look at example 4. I've got two functions. You are going to have to write this one in. F of x equals the square root of x. And then g of x is x minus 1. So we're finding f of g of x, and we're stating the domain. F of g of x would be f of x minus 1. So that would look like the square root of x minus 1. Well, if that's the case, if that's my result, I know my domain, x minus 1, has to be greater than or equal to 0. So x would be greater than or equal to 0 plus 1, which is 1. Okay, so there you have it. This is the result, and this is my domain. So your domain would be from 1 to infinity. All right, other compositions that we can do, finding g of x. So this is just saying do g of x minus 1. You're substituting x minus 1 into its own function, so you'd have x minus 1, and then minus 1 again, which is x minus 2. Both of these are linear equations. Your domain, it's a polynomial from negative infinity to positive infinity. Okay. Finding f g of 2. F of g of 2. Well, this is f of g right here. F of g was equal to the square root of x minus 1. So I'm going to evaluate 2, which would be the square root of 2 minus 1, which equals the square root of 1, which equals 1. Result, f of g of 2 is 1. And finding f of g of negative 1. Well, I can't do this, and the reason why I can't do this is because my domain, the domain for the composition was from 1 to infinity. I can't substitute negative 1 in if it doesn't lie in the domain, so this is undefined. So again, composition of functions is a matter of substituting one function to another and simplifying it and trying to figure out their domains. All right, example 5, I'm going to challenge you a little bit here. It says if you have h of x is x plus 1 squared minus x minus 1, find two functions f and g such that this is the composition f of g. What you want to do is go back to your original function. You can see here I've got an expression being squared here. Well, if I'm substituting a function in and I'm getting this as a result, this must be an x squared. Okay, and that means I've substituted x plus 1 in. So I'm going to conclude that g of x must be x plus 1, and I'm substituting that in. So how can we make this expression in x plus 1? By factoring a negative out, you get x plus 1. So f of x has to be, you got the x squared from the beginning, and then you got minus an x. You can always double check this. Let's go ahead and look at what our results would be. If I do a composition, if I find f of g of x like this, then I would have x plus 1 squared, and then minus parenthesis x plus 1, and you can see after distributing, you would get minus x and minus 1. So this does give us the original here. So you're going to have to look at that and try to just logically figure out, where can you do some substituting and what is your expression. All right, last example here, we've got an application problem. It says the weekly cost of manufacturing a certain product is given by C of X. Cost here of manufacturing a project. The number of units X produced in T hours is given by X of T is 3T. Find and interpret C of X. So this is asking to do C of 3T. C of 3T would equal 25, put in 3T, plus 5,000. What does this mean? So this is 75T plus 5,000. First of all, the C is still cost, and the T is the number of hours. Okay, so if I'm interpreting what that means, it's the cost after T hours. Cost after T hours. And finally, last question, how many hours will the weekly cost be equal to 10,000? When does this equal 10,000? So when does the 75T plus 5,000 equal 10,000? Subtract 5,000, divide by 75, and you get the hours would be equal to 66 2/3. That's how long it would take to cost $10,000. And what we did here was we did a composition. We put the function of x into your variable so that we could get cost and time written together. All right, this is your assignment for section 5.